Hi guys, so what we're looking at here is the proof of the theorem, Chord theorem, right? So this is one of the Euclidean proofs that we need to know, and they can present this in a couple of ways in the exam. So they could present it like this: they say, prove the theorem that states PAB is equal to ACB, or they could say, prove Chord theorem, right? They could say, use the diagram to prove the theorem that says the angle subtended by a chord is equal to the angle between that chord and the tangent. So whichever way they give it, we need to know how to do it. So we must recognize this diagram, and we must know that we need to prove Chord theorem when we see this. So these angles over here, PAB, that's this angle over here, PAB, okay, that's that angle right there, and ACB, that's that angle right there. Okay, so we need to make some constructions like we normally do, and then solve our way from PAB back to ACB. And what we're going to use here is we're going to use the center, we're going to use a radius, okay, and we're going to use angles at the center, okay. So sometimes they'll give you the center here and sometimes they won't. We're just going to draw that center in, okay, and we're going to label it O. So we are going to construct, and it's a good idea to label your constructions like this, declare them like this, but you don't necessarily have to, so don't worry too much about that. If you feel like that's going to be difficult to remember, we're going to construct O, the center of the circle. Okay. So we're constructing O, and then we're going to construct our radius, OA, and we're going to construct OB. And if you notice here, what we've done is we've already kind of put in this angles at the center and angles at the circumference sort of diagram. So if you focus on that arrow shape there, we've got angles at the center here. Okay, so we constructed OA and OB. Right, now the next thing is going to be to label an angle. And what I'm going to do here is I'm going to let OAB, so this angle over here, I'm going to let it equal to x. Let OAB, angle OAB, equal to x. That's this angle over here. Okay. And then right away, because we have this isosceles triangle here with equal radii, right? That means that OBA is also equal to x. Okay. And there is a reason for this. The reason is radii. Okay, now before we go any further, it's going to be important later on down the line that we know what BAP is. So let's start off here by just stating that OAP is 90 degrees. Okay, that's OAP over there. OAP equals 90 degrees. And why is that? That's because we've got a radius and our tangent, PQ. So the tangent is perpendicular to the radius. Okay, cool. Now, what that means is because this angle is x, and we've got this 90 here, we can say that the rest of this angle is 90 minus x. Okay? So I'm going to label that 90 minus x. That's that part of the angle there. And that is angle BAP. So we're just going to write that down. It's basic geometry though, so we don't need a reason there. BAP is 90 minus x. Okay. And when I say basic geometry, it's like it's evident there. We've got the 90, we've got the x. these two add up to 90. Okay. The next thing is inside this triangle over here, we need AOB. We're going to need this angle AOB so we can take it back there to the circumference. And what it's going to be is just 180 minus 2x. That's the sum of the angles in the triangle. All the angles should add up to 180, so we can say that it's the total angle is 180 minus these two. Okay. So that angle is AOB or BOA. Remember they're the same. That is 90 minus 2x. Oh, sorry. That is going to be 180 minus 2x. Okay, this angle here is actually AOB. Right. I want to label it properly. AOB. Okay, so also let's write that in on the diagram. And then finally, we are going to take this back to the circumference here. And we know that, oh, we have to have a reason here as well. So this is sum of angles in a triangle. And now we've got 180 minus 2x over here. When we use angles at the center, we're going to halve that. So a half of 180 is 90. And a half of 2x is x. So this becomes 90 minus x. And you recognize that it's the same as BAP, or PAB, as we labeled it originally. So let's just write that out quickly, and our proof is nearly done. So ACB, which is this angle from the beginning, is also 90 minus x because of angles at the center, and this is a long one, angles at center equal to 2 times angles at circumference. Okay, and we can go right ahead and say that's equal to PAB. Which was our original mission. And that's the end of the proof. Okay, so just to run through it one more time, because there's quite a few things to remember in this one. We have to construct the center of the circle if necessary. We construct radii OA and OB. We also label those as equal radii so that we can see the isosceles triangle there. Okay. We let this angle equal to x, OAB. Now it's also possible to let this angle equal to x. So if you see that as in one of your proofs, if you see this as x and this one as 90 minus x, I wouldn't worry too much about that. It works out almost the same way. But if this angle is x, this angle is also x. Okay, that's OAB and OBA, they're both equal to x. OAP is a right angle, right? We need to remember this supporting theorem, tangent perpendicular to radius. Okay, then using sum of angles in a triangle, we end up getting this angle at the center, AOB, and using that angle at the center, we take it to the circumference, at which point we see both of our 90 minus x's there. So try and work through this a couple of times, show your steps, practice doing the constructions, and just, if you can, my advice for all of these proofs is often just to try and do everything on the diagram and then use that diagram to write out the formal proof.